quantum computers are able to solve certain problems more efficiently than their classical counterparts. Some of these problems are even relevant to big industries such as logistics and pharmaceuticals, so that both states and companies have made huge investments in the development of such devices. This in turn brought the topic to the attention of the mainstream media. Yet when it comes to explaining why quantum computers can outperform classical ones, most explanations I've seen, both from journalists and scientists, have failed to mention a key ingredient that allows us to go beyond what we once thought to be the limits of efficient computation. Now, if you already spent some time learning about quantum mechanics, you probably came across concepts like superposition, often introduced with the thought experiment of Schrödinger's cat, where the cat is said to be simultaneously dead and alive, or more scientifically, through the double-slit experiment where particles like electrons seem to interfere with different evolutions of themselves by exploring all possible trajectories at once, a behavior that is often used to suggest that quantum computers can parallelize some calculations. You may also have heard of quantum entanglement, where measuring a particle on one side of the galaxy immediately determines the state of its entangled partner on the other side, a kind of non-local correlation that Einstein famously called spooky action at a distance. Now, with such amazing effects in their arsenal, it may seem obvious that quantum computers, by superimposing many calculations at once, can outperform classical hardware. And that's the kind of narrative one consistently encounters. In reality, however, neither entanglement nor superpositions are sufficient to achieve our desired quantum advantage. This fact is neatly captured by the Gossesman-Nil theorem that states that quantum circuits only consisting of so-called Clifford gates can be efficiently simulated on a classical computer. Now, I'll spare you the details of what exactly a Clifford gate is. You may look that up on Wikipedia, and simply tell you this. The Hadamard gate, the quantum operator that creates superpositions and lets your quantum cat be both dead and alive, is part of the Clifford group. And so is the CNOT gate, which together with the Hadamard can bring two qubits into the maximally entangled Bell state, whose verification received the Nobel Prize in 2022. And yet everything built from these gates can still be efficiently simulated on classical hardware. That's not to say that these gates aren't important, they show up in almost every quantum circuit, but they're simply not enough to achieve the kinds of breakthroughs that would justify the millions of dollars being poured into quantum technologies. The missing ingredient for the quantum magic is called contextuality and is actually related to something known as magic states in quantum information. Contextuality refers to a quantum system where the outcome of a measurement cannot be taken as predetermined, but instead depends on the context of what else is being measured. As an analogy, imagine you're handed 3 boxes. If you open boxes 1 and 2, you find a red marble in box 1 and a blue marble in box 2. However, if you open boxes 2 and 3, you may find a red marble in box 2 and a blue marble in box 3. Classically, that's nonsensical. The marble in each box should be either red or blue, regardless of what other boxes you look into. Yet there is a method to the madness. If we go back to our analogy and now open boxes 1 and 3, we would again find a red and a blue marble. Suppose that there is a rule that each pair of boxes must reveal both colors when opened. Given this rule, you can quickly see that there can be no fixed assignment of marbles to boxes. Assume, for example, that there are blue marbles in boxes 1 and 3 and a red marble in box 2, then opening boxes 1 and 3 would break the rule. Such contextual rules are actually found in quantum physics, though instead of marbles they regard observables, meaning measurable quantities of a system. A commonly studied example features 9 such observables, each taking the value +1 or -1, that can be arranged in a 3x3 grid known as the Merman-Paris magic square. For a macroscopic system, you may think of these observables as yes or no questions about physical properties, questions you'd expect to have a definite answer whether or not you check them. But the laws of quantum physics can impose global constraints, for example that the product of the observables in each row must be +1 while the product in each column must be -1. It's easy to show that no fixed assignment of values can satisfy both conditions at once. So the values of these observables aren't simply waiting to be discovered, but only become definite through the act of measurement, and their outcomes depend on which set of observables, row or column, you choose to measure. Furthermore, quantum theory only allows certain observables to be measured together. So when measuring the observables of, for example, a column, the system will be altered so that follow-up row measurements will not correspond to observations of the original state anymore. Put simply, in such quantum systems, a measurement doesn't reveal pre-existing properties, but instead creates them according to their context. Now, after hearing about superimposed cats and entangled coins that always land on the same side, this might seem like just another quantum weirdness. Yet it is worth highlighting that neither superpositions nor perfect correlations themselves are uniquely quantum and can also be found in classical systems. Contextuality, however, contradicts the classical assumption of realism or value-definedness, the idea that measurement outcomes are based on previously existing properties of a system, and in a sense used to draw the line between classical and quantum information theory. This observation goes hand in hand with the aforementioned Gottesman-Nil theorem, which tells us that quantum circuits only featuring Clifford gates, which can create both superpositions and entanglement, can be efficiently simulated classically. In fact, as shown in this paper from 2014, all quantum algorithms that offer a relevant quantum advantage feature contextuality. Such contextuality is, for example, introduced by the Non-Clifford T-gate, which applies a 45-degree phase shift to a qubit. Applying such a T-gate to a qubit in a superposition yields the canonical magic state, which is used in many quantum computing schemes and displays contextuality with respect to a cleverly chosen set of observables. I again want to stress the point that we are only able to go beyond the scope of classical computation when including quantum resources that exhibit contextuality, states that are fundamentally incompatible with the classical assumption of value-definedness. One reason why this concept is so frequently overlooked by people without a quantum information background might be that it is often difficult to see where contextuality enters a given quantum circuit. In Grover's algorithm, for example, such non-Clifford gates only appear in the implementation of the oracle function, which is usually not shown explicitly. In Shor's algorithm, contextuality enters in the modular exponentiation subroutine, which again is easy to miss. And the same is true for many quantum circuits. Contextuality is there, but tucked away in some corner of the implementation. Even if you have never heard of these algorithms, the takeaway simply is that contextuality often feels like a minor detail within them. And it is indeed not fair to say that non-Clifford gates or contextuality in general do all the heavy lifting in a quantum circuit. Instead, I would think of them as portals to the quantum world. If your calculation never passes through one of these portals, then tools like the Hadamard and the CNOT gate remain confined to classical limits. At this point, you might wonder how exactly contextuality helps in a computation, which is an intricate and still partially unresolved question, one that I won't attempt to answer here. The purpose of this video is more to clear up a common misconception about what makes quantum computing special in the first place. You see, classical devices are bound to non-contextual logic, where variables have objective values. Quantum systems, in contrast, allow for a more general kind of logic, where what's true and false can depend on the global context. So the next time you hear about quantum computing, think of devices that harness contextual relationships where the value of a quantity can depend on how it is embedded in the computation. That's where the real quantum magic lies. Thank you for watching, and there's additional material in the description.